Good morning, everyone. Welcome and thank you for joining us for the AI-powered build, generative design, robotics, and automation in the future of construction. My name is Joe Broon. I'm the Managing Director of Building Digital and today's host of this online micro conference. Today's session explores one of the most important shifts our industry, every industry, has ever faced. How artificial intelligence is moving from theory into real-world application across the entire construction life cycle. From generative design tools that reshape how we conceive buildings to robotics and automated systems that are transforming how we physically construct them, AI is redefining what's possible. Across this session, you'll hear from leading innovators working at the cutting edge of design technology, robotic fabrication, and intelligent systems. They'll share practical insights, real-world applications, and forward-looking perspectives on how these technologies will shape the future of architecture and construction. Next, we move on to Mollie Claypool. Mollie is the co-founder and CEO of Automated Architecture, or AUAR for short, who are a pioneering company developing robotic micro-factories for the automated construction of low-carbon housing. With a background spanning architecture, computation, and robotics, Mollie's work focuses on making advanced manufacturing accessible, but also scalable within the built environment. He's been widely recognized for bridging design and automation, and is a strong advocate for rethinking how we deliver housing through distribution, AI-enabled construction systems. Mollie, are you free to take over the screen with your presentation, please?
Great, amazing. I'm assuming you can see it.
Yes.
Great, cool. So I'm just going to start with a kind of thesis and then go into how we kind of address that thesis. So our starting point at AUAR is that the housing crisis is in part a manufacturing crisis. You know, we've kind of solved the problem of beautiful housing, right? But the problem ultimately around being able to deliver that beautiful housing, those good homes, is delivery. And when we look at the industry and we look at home builders, there's kind of a three-way dilemma. If you add more labor, that labor, generally speaking, is very scarce and getting scarcer. If you look to going to a panel supplier, there's a lack of control that happens. You essentially go into a queue and there's a black box behind that, wall when you make that order. Or the third option is essentially building your own factory in order to deliver homes, which is unrealistic for about 99% of builders, generally speaking. So this is a problem that's ripe for automation, and it's ripe for robotics. And ultimately, construction is really the hardest robotics problem to solve. And we're seeing now a lot more robotics investment, and capital is really starting to flow into the industrial automation space. But that capital ultimately has been concentrated in places like logistics or warehousing or last mile delivery or healthcare, which is very clean environments, very controlled environments. And so construction really remains that last gap. And that gap exists ultimately because the problem is hard. And that's exactly why at AUAR we think it's really worth solving and why it's most interesting for us. And we think that the harder the environment, the more rewarding it is to solve. And then there's also kind of two kind of general theses, I would say, around robotics, generally speaking, which is one is around generalist robotics. You could include humanoid robotics in that batch. But humanoid robotics ultimately need those very uniform and controlled environments. They need really consistent materials to work with. They need fixed and repeatable tasks. They need to scale by replication of those exact tasks. Whereas in construction, every site's different. Material varies, right? In our case, we work with timber. You have bow, you have twist, you have moisture. You have what we call beaver wood, where you have entire cuts taken out of the wood in a stack. You have a kind of reality in construction where most projects are kind of resetting from zero when it comes to the data that's driving those projects. And ultimately, their domain knowledge, deep understanding of how construction works is the unlock. So how can you work with that domain knowledge rather than working against it when you think about a solution that integrates robotics? So our thesis essentially is that we have to develop robotics that has vertical domain specificity. And that essentially means that the harder the environment is in terms of like how that vertical is defined, the harder it is to replicate what you learn inside of it. And our product that we have developed at AUAR is essentially a manufacturing solution for, I would say, the kind of foundation of any building, which is its structure, not the actual foundation, which is a production thesis around deployable manufacturing. What if you can bring, the automation to the site, to where buildings are being built? And how can you do that then in a way that really works with the distributed nature and fragmented nature of construction? So ultimately, our microfactory enables factory output, but without owning a factory. And because it's deployable, it can move with projects. This is important because essentially homes are local, homes are everywhere, homes are distributed. If the next best alternative is a fixed factory, that concentration of risk means that the way that the industry works doesn't really match, because if demand changes, you're ultimately stuck. So our microfactory is containerized. It shows up, it sets up in hours, and it replaces a very clear line item in the delivery problem, which is the core and shell of buildings. And ultimately, it can move with demand. And then what this gives you is essentially a kind of 3 points of domain specificity. One is that it's developed specifically for the problems it's solving. So it's purpose-built for timber frame. It enables, dual-sided assembly. It enables automated crowning. It enables code compliance, variable handling of different kinds of materials. And generalist robots really can't replicate that. It also has behind it a physical AI that learns from that variability, that learns from that difference, and kind of adjusts in real time and builds behind it a data set that makes any system that we're working with much more reliable across all of the units that we have deployed. And then what it also does is it embeds that operational know-how. So everyone we work with, every partner that we have, we deepen that learning by documenting and using that data as a way to accumulate knowledge. And that accumulation of knowledge means that we essentially build out a data set that's not public, but is able to be used across any place where we're deployed. And so our kind of like overarching idea here is that, in order to bring a better method of delivery into construction, you don't sell the robot, you actually sell the output, the industrialized production. I'm just going to skip through a few of these things here because I'm going to get into kind of more of the nitty-gritty. And essentially behind that is a system that reads the material in real time all the time. And this is why we argue at AUAR for the idea of physical AI. So it handles timber variates. It doesn't work just with assumed geometry. There's sensing and vision embedded in this that allows everything that's happening in the physical world to inform the data that underlies and loops back from the digital to the physical. What this also means is that we can cut costs, we can increase control, we can create homes at a much faster speed as well. And then behind this is a kind of intelligence layer called Master Builder. So Master Builder is an end-to-end software platform for timber frame manufacturing, and it takes a building design and transforms it into a manufactured panel, whether that panel is being used for a wall or a floor or a roof. And it kind of spans design input, data processing, operation, and physical hardware control. And the way that these designs enter Master Builders through dedicated plugins that we've developed for Rhino and Revit, and these essentially translate 3D geometry into our internal data structures and generate the kind of fasteners that connect each of the panel elements together. Behind this is a link ultimately between the kind of shared contract layer across the entire stack that we've developed. And there's a series of operations from a single source of truth, and runs in essentially 3 steps. So there's a building system solver that essentially resolves the design against building system rules. So those can be code-based rules, they can be manufacturing-based rules, and it essentially produces a fully defined panel. And then there's an assembly graph generator that then produces a directed graph of all of the elements and their connections with all of the sequencing that defines the kind of physical assembly order. And then finally, there's a third part, which is a program generator that takes that graph and produces a JSON file. And that's the manufacturing instruction that encodes kind of pick positions that the microfactory uses to do the assembly, including all the placement targets and all the other operations that happen in the physical world. And that pipeline also outputs things like bills of materials, exact costing data that can be linked to supply chain, material takeoffs, and IFC exports, just from the same exact model. And our argument there is that essentially that gap that exists in construction and design, like the gap between design and a built project, is really only a software problem. So we have to ultimately create that feedback loop and that link back and forth. And what that gives us as an industry is essentially this end-to-end workflow integration where every home exists as a digital simulation in full from design to production as much as it exists in the physical world once it's built. And what does that mean for us? It allows us to also continually stress test, all of the unit economics for not just the people that we work with, but for ourselves as a business, so that we can identify opportunities to learn and optimize on throughput, speed, quality, operation, everything that kind of comes in as a point of data in the system. It also means that we can, we've kind of scaled the microfactory to being able to do, full scale building elements. So you don't need to make sub-assemblies separately, just one go. We've been operational with some earlier versions of our microfactories in Belgium and in the US as well. Oops, that didn't play automatically. This is an early version in January 2024 that built a couple of projects. I might have time to show them in a second. And this is two versions that we also had in the US that are being replaced imminently, actually, that have been building homes over the last almost 8 months. Some of the things here that we've kind of trialed and had trials and tribulations with was, how do you take the quality of American lumber, which there was a stack here somewhere, but I think I might have deleted the slide, take the very low quality of American lumber and turn it into a really high value panel. How can you then use the software to define, what is the overage that you need for materials? How do you reduce waste? How do you essentially optimize panel assembly to get the most out of what you're doing, which enables you to reduce costs, reduce waste, and also reduce carbon emissions overall. What's interesting here for us is that essentially, we're providing the kind of system behind the homes that are being built using our products. So, this is one example of a public housing procurement framework that we're on in Belgium, where you have a kind of brick slip facade house, but you can also have, for example, single family and low rise multifamily. The system behind both of these types of buildings is exactly the same, but it enables kind of that variety and customization that's needed by either architects, designers, or demanded for by sites. One of the other propositions that we've put forward into the world recently is then how do you actually do timber frame at mid-rise scale? This is really important if we think about alternatives to concrete, because we need to start densifying our cities. What we got to here is that essentially, if we use the building system that we've developed for mid-rise with our microfactory, we can cut carbon, cost, time, and provide a very a really, really good competition to something like CLT or mass timber. And what this also opens up, we would argue, is that if we address the kind of domain specificity that we need in construction, we can also think about, who are the people working and using these new kinds of technologies in the industry. So our thesis is that we develop a platform for a new kind of builder to emerge. Not someone who's a laborer, not someone who's necessarily an engineer, but someone who becomes a manufacturing specialist, but doesn't have the kind of requirement of having knowledge around automation or robotics. And a lot of this has to do with how we actually develop our UXs, our training, and how we also deploy on site. So for us, we don't sell our technology to the customers that we work with. We actually provide we act as a subcontractor. So we provide the operator, and therefore through that operation by us, we can also train our partners and customers to eventually also operate those microfactories and build out their own new kind of workforce. And essentially what this brings together is that essentially every single time we deploy, every single time we process a design through Master Builder, every single time we do a test or build anything, it makes everything better in the system because there's that end-to-end feedback loop. So ultimately, really, this bottleneck shouldn't ever really be considered the robot. It's really the system. It's how do you accumulate domain data? How do you capture that? How do you embed the know-how? How do you create partnerships that enable that integration depth? And how do you consider software as an intelligent layer? And there's been kind of three main ways this has been tried before, which haven't worked. You've got machine builders, you've got centralized offsite companies or startups, and you've kind of legacy on-site construction. But all of them share ultimately the same flaw that they're only thinking of the unit of scale being the building, not the intelligence behind it. So what this opens up, I would say, for architects is design complexity. Like the microfactory adapts, not the design. What actually gets drawn can actually get built. For builders, it allows us to open up factory quality production on site, with precision manufacturing. For the industry, it opens up the notion of a distributed network. And for communities, it enables the thing that we all need and want, which is good homes everywhere that can be manufactured on demand, and for the cost that is accessible. So thanks very much.
Thank you, Molly. Very, very insightful. Thank you very much for your presentation, following Cesar's. Really interesting stuff there, guys. I can see a couple of people there doing the applause sign. So thank you, Molly. Before I come to a couple of my questions, I'm hoping there should be some questions from some of the attendees. So I'll open it up to questions. Have we got a question for Molly, please?
I can ask one. While waiting for people. You
Go on,
answered a
Gillian.
lot of my questions. Yeah, sorry, Gillian Ashworth here from Building Digital. I'm the events manager with Joe, and it's just you've answered a lot of the questions that I was sort of thinking about as you were going along. To be honest, Molly, you've obviously done this before, so it's just a quick call, really. I mean, it's just quick. How far have you come to introducing this in the UK, and is it viable for housing associations? That's kind of always something that everyone sort of asks for these sort of new construction methods. So just thought I'd ask that at the start.
Yeah, I mean, until quite recently, we actually had no activity here in the UK. But over the last couple of months, we've signed our first partner. And so we'll be starting to build projects this summer in the UK.
That's good to know.
Yep. We're actually the thing about housing associations is that you have to get on the procurement framework. So because we operate as a subcontractor, that is something that we are looking at. And we're working with various organizations who can help influence procurement decisions to be able to do that.
Yeah, understood. There's always a bit of red tape with the UK, I guess. I gotta get around that.
Yeah, I mean, we tend to work with self-performing builders because that enables us to circumnavigate that problem for now, but that's not the long-term goal.
That's great. I'll let them go now since some stuff come through the chat, so I'll let Joe get on with it.
Yeah, we have had a couple of questions through the chat. The first one of which is from Laura Proctor. Laura is a principal engineer at Atkins Realis. Laura asks, you mentioned that the microfactory is designed for timber frame construction. Is there feasibility to extend this to steel structures or reinforcement prefabricated structures?
Yeah, I mean, the microfactory is designed in principle where we could do light gauge steel, but it's not on our short-term roadmap. When you run a startup, you have to focus on one kind of product vertical. So we're focusing on timber. Our mission is to make sustainable housing universally accessible. And I would argue that there's a sustainability question around steel, even if there still is an application possibility and opportunity there.
Good. I hope that answers your question, Laura. Moving on to Michael McSorley. Michael's the project manager at WSP. Michael asks, how does the containerized assembly or assemble robot operate in terms of the site weather environment and health and safety segregation? And where are the microfactories housed?
In a tent shelter. We actually deploy two containers. One makes one side of the factory space, one makes the other side of the factory space, one sets site office and storage, and the other one is for materials storage as well. And then there's a tent that goes over it. In terms of security, it's actually the most valuable thing in any robotic setup is actually the plug. That can be removed overnight and locked away. Everything else is actually very difficult to take away and remove. So security is the biggest thing that we have to deal with, is actually making sure that that can't be turned on. Yeah, so pretty straightforward in a tent.
Yeah, sounds good. Next question is from Alexi. Alexi is the mechanical engineer over at Cooper Homewood. Alexi asks, what are some of the logistics concerns, environmental challenges you have to face when having the containers be delivered on site?
I mean, we have a minimum site setup requirement. The major thing is actually just having compacted ground. So that can be gravel or asphalt. In some cases, people are pouring a slab for us to sit on. So that site readiness is important, but we have a couple of different layouts that we use for how we get the microfactory stood up. And how logistics are operational. We actually, once materials are delivered to site, we own everything else until the panel packs are delivered to the assembly contractors. So that's on us, and we take on that responsibility and risk, and we're experienced in doing that.
Good stuff. Will answer your question, Alexi. Alexi and Kevin Fielding are going to get gold stars for their participation with questions for today's meeting, I think. So we've got a question from Kevin Fielding, who again is an engineer, I believe, from Shepherd Robson, or an architect. Kevin asks, for mid-rise housing, how does the offsite manufacturer cost compare with concrete frame?
Yeah, so we are 4% cheaper than concrete.
Excellent. And he also asked, do you envisage, he's got three questions, so this is the second one. Do you envisage this ultimately extending to individual homeowners, or are you looking solely at scale?
For the next few years, solely at scale. We're working with builders doing anywhere between, our minimum in the UK is around 100 homes a year. So we're working from that as a minimum upwards at the moment.
Just looping back to that kind of MVP and being a startup, isn't it? And then final question he's got is, do the panels also include insulation?
So we're agnostic to insulation purposefully, because if we started to be specific to insulation, we would actually cut down our market reach, who we can work with. We can pull the panel off, have installation be installed, and then pull it back on, or have it be pulled off for installation to be put on and for a panel to be closed. We're looking at, would we automate that in the future? Right now, our assessment is no, because we do want to remain agnostic. We're working across the UK, Europe, US, Canada. There's a lot of different positions to how you deal with insulation. So it really depends on how the partner's set up and how much finishing they want to do before they take a panel to site. We most often work with one side closed and open frame panels.
Okay. Another question from Amos, who is an architect at ASB Architects. Amos asks, what is a realistic or practical timetable for a 4-story house from start to finish, whether permitted, training a new team, etc.?
So to produce the structure for a typical 2-story, 3-bed, say, terraced house is a day to produce the panels for it. On site to do assembly, a couple of days. We don't need to train a new team. So we have our own team that does that production. And then the panels are just like how any builder would receive panels from any other panel supplier. So as long as they're working with a team that's familiar with that, we're good. It's really just about instructions if you don't have experience doing that.
Wow, some pretty transformational stuff, Mollie. Brilliant. I think we run out of questions. Yes. Thank you, Mollie, for a fantastic presentation and for taking the time to answer those questions quite comprehensively. Before we wrap up completely, I'd like to briefly reflect on our 4 keynotes today and some of the key insights from today's session. Firstly, we heard from Cesar Fagachan Pinzani from Alta. Cesar showed how AI is transforming early stage design through digital twins, configurators, and automation. His platform enables real-time exploration of building options while staying connected to cost, materials, and delivery constraints, which in turn helps to bridge the gap between design and reality. He also highlighted a key challenge: adapting to different workflows across practices and driving adoption. Alta's approach combines open source AI with bespoke solutions, supporting everything from student housing to customized residential projects. Our second keynote was Mollie Claypool from AUAR. Mollie reframed housing as a manufacturing problem, presenting AUAR's robotic microfactories that bring production directly to the site. These portable systems deliver factory quality timber construction without the need for permanent facilities, powered by software that link design straight to manufacturing. By combining robotics with physical AI, AUAR is improving speed, cost, and scalability, offering a practical new model for delivering housing at scale. We then moved on to Loris Di Natalia from Zurich Soft Robotics. Loris introduced Solskin, a responsive facade system using soft robotics to optimize energy, daylight, and comfort in real time. Rather than relying on complex rules, the system uses AI to learn from user behavior and adapt over time. Built with resilient pneumatic components, it offers a flexible and modular approach to intelligent building envelopes, while highlighting the broader challenge of balancing user needs, energy goals, and system integration. And then we just heard our final presentation today from senior lecturer at Loughborough University, Shirin Dora, who focused on AI in project controls, showing how it can transform how we manage construction data. His system, construction.ai, connects information across documents to detect risks early and predict their impact on time and costs. It shifts teams from searching through information to simply asking questions and receiving clear, actionable insights. Trin's case study presented strong accuracy, pointing to a real opportunity to improve decision making and productivity across projects. So, thank you for attending today's micro conference. I think taken all together, today's speakers have shown that AI is not just a future concept, it's already reshaping how we design, build, and manage the built environment. The challenge now is how quickly and effectively we can adopt these tools to unlock their full potential. Thank you again to all our speakers and to everyone who joined us today. Please do keep going back to buildingdigital.com. Thank you again from me, and enjoy the rest of your day. Thank you very much.